Well, good evening, everyone. Welcome to Monday Night Calculus. Sorry for the late start. I guess it's very cold up in the Northeast. Some of those internet lines are frozen. My name is Steve Kokoska. I'm with my colleague Tom Dick, who's up in Oregon. And behind the scenes tonight is Michelle Morgan, our technical, spiritual, and YouTube advisor, is helping us tonight. She'll take care of the chat. We're going to do a little bit with particle motion. As usual, we've got a couple of questions that we have posted on the Facebook site. And Tom's going to do some technology. And please, if you have any questions, please put them in the chat. I think that Michelle will be monitoring that and she'll forward those on to us. Michelle, please feel free to interrupt us at any time. All right, so here we go. The first one is there are two toy cars labeled A and B, and they're traveling along the straight track for 8 seconds. So you can kind of think of this as a racetrack with two cars side by side. So both start at position 0 at time t equals 0 seconds. And this is a very typical sort of AP problem here. The graph of the velocity for car A is given, not an analytical formula. So the graph of the velocity v sub A of t, which is measured in centimeters per second, is given in this figure. Kind of nice. This is made up of straight line segments, and we'll talk a little bit more about graphing that, and maybe Tom will do a little bit with that also. The position of car B at time t is given by this expression. So for car B, we have an analytical expression for its position, and we've got lots of questions that we want to answer about this setup. So first of all, find the velocity and the acceleration of car A at time t equal 3 seconds. And let's not forget about the appropriate units, I guess. So let's see, the velocity of car A at 3 seconds. Well, in order to get that, I've got to go up to the graph here. So I'm going to go at t equal 3, and I'm going to go up to the graph, and I can see that that intersects at, I think it's v equal 25. And let's see, the units here, and I've got to check this carefully. I've left a little bit of room for myself here. The units, I think they told me up here, was centimeters per second. And the acceleration, well, that would be the slope of the velocity curve, and we're lucky in this case. Remember, we don't have an expression for this, but this is a straight line segment, so we can measure the slope of that straight line. And I did that by taking 2 points on the curve, I think 440 and 210, if I did that correct. And so I got the acceleration as 30 divided by 2, the slope of that line, and I think the proper units there would be centimeters per second squared. How about that? So cool, very typical sort of an AP problem. Tom, back me up on this one. Very typical to see a graph and ask students to read from the graph to find the slope of a straight line in there. I think that's common.
Yeah.
In part B, yeah. Find the velocity.
So Steve, so you're quite correct about this type of problem. I think is very popular on the AP exam, where the students are provided a graph,
Yep,
and asked to reason kind of directly from the graph. A teacher using this in the classroom, while still emphasizing that, and in fact, it would be this type of question would very often be on the non-calculator part of the exam. But nevertheless, the teacher might want to use the calculator to discuss the problem, and it might want to reverse engineer that graph and get it on there. So at an appropriate point, I was just going to show folks how to do that on the 84. But I'll leave it to you to when that's a good time. Okay.
Okay.
All right.
Okay. Deal. All right. So in part B, let's see. Find the velocity and the acceleration of car B at time t equal 3 seconds. Well, okay. Once again, we have the formula or the analytical expression for the velocity of car B. Or pardon me, I beg your pardon. We have the position of car B. So we've got to find the velocity. So we take the derivative. There it is. There's a constant 6 out in front. And we just need to use the power rule. So bring the power down 5/3 times t to the 5/3 minus 1, t to the 2/3. I think I did a little bit of simplification there. So there's an expression for the velocity. And we want the velocity of car B at time t equal 3 seconds. So I'm going to plug in a 3. And I'm going to show you some calculator screens on the Nspire in a minute. And Tom will probably do some work with the 84, but I got a numerical approximation here of 20.801 centimeters per second. In order to find the acceleration of car B, well, I've got to take the derivative of the velocity. There's the constant 10 out in front. There's the power 2/3 times t to the 2/3 minus 1. And I did a little bit of simplification here. Hope I did that right. 20 divided by 3 times the cube root of t. I want the acceleration of car B at time t equals 3. I've got to plug that in, plug that 3 in. And again, numerically, I think that's a 4.622, and I think the units are centimeters per second squared. Now, let me show you a little bit of technology on the Nspire, and maybe we can take a TI-84 break here. Let's see what happens. So up in the top left-hand corner of my screen, that's on a calculator screen, and you can see that I can define a piecewise function on the TI-Nspire. I'm not going to go through the keystrokes here. I'm going to show you a lot of screen illustrations. We understand that the majority of you perhaps probably use the TI-84, so Tom will be a little bit more explicit about that. But you can very nicely define a piecewise defined function, and there it is. And as Tom said, what I did is sort of reverse engineer those straight line segments. And to be careful about the intervals, find the slope, find an equation for the line on that interval, a particular interval. And there's my piecewise defined function. And just to double check, I graphed that over here on the right-hand screen, and it looks a lot like what I presented on the first screen tonight. Down here on the calculator screen, I also defined the position function for particle B. It looks kind of funny. It's got that left curly bracket there, but only one interval. I think the reason for that is because I wanted to define the position function of B only on this interval 0 to 8. And so that's why it's showing up in this curly brace. It's kind of a piecewise defined function, but with one piece. Okay, so to check a little bit of this with technology, we needed the velocity of car A at time t equals 3. Well, there it is. I think I got 25 on the first page by interpreting the graph. I needed the acceleration of car A. Well, that's the derivative of the velocity at time t equals 3. Sorry, I'm going to draw a couple of arrows or an arrow in here. You can probably see that little vertical bar in there. So we often read that when we write with a piece of paper and a pencil as such that, at least that's the way I often think of it. So that's kind of telling the calculator, find the derivative of dA of t with respect to t, but after you find that, such that use t equals 3. And I got a 15. I think that's what I got on the previous page. So I'm feeling pretty good about that. Now, remember, I've got an expression for the position of particle B. So let's see, here's the derivative of that position function at 3. So that's the velocity of car B. There's the exact symbolic answer that we got on the previous page. There are many different ways here to find that, to convert that into a numerical approximation. Here is a way to do it. Do the exact same calculation, but put a decimal in there. Evaluate that at 3 point. And 20.8001 if I were to round off and not truncate. And I'm sorry about this, but down at the bottom here on the right-hand side, there's the acceleration of car B at time t equals 3. There's the exact symbolic answer. Might not look exactly like what we got symbolically. In fact, it doesn't. This is often common. Sometimes the calculator gives us a little bit different expression, a little bit different form of the answer, but that's the right answer. I wonder if you can convert that. And I want the numerical approximation, so I just took this answer and multiplied by 1 dot to convert it to a decimal. And there's the 4.622. I think that's the correct answer, rounded. Pretty good. Tom, how about if I just finish this one and then I'll hand it over to you for the 84? Is that all right?
That sounds great, Steve.
Okay, good. All right, so part C here, this is a really cool problem, I think. Lots of neat questions in here. Which car travels the greater distance between t=4 and t=6 seconds? And justify your answer. So which travels the greater distance? So when I read that, I had to think a little bit about, well, the car could go forward for a while and then backwards for a while. I need the total distance traveled. That's the way that I interpreted that. So here's what I realized as I started to solve this. Car A is traveling at a constant speed of 40 centimeters per second over that interval 4 to 6. How did I know that? Well, I found that by looking at the graph. The velocity is constant, positive, greater than 0. It's always traveling in, well, okay, the positive direction. So this is pretty easy to figure out. The total distance that car A travels is the velocity times the time. So it's just 80 centimeters. Now, for car B, the velocity is also always positive. How do you know that? Well, you can see that by looking at the analytical expression for the velocity, but just to double check this, what I did is I'm going to draw an arrow here. What I did is I drew a graph down here or on a graph screen. I have the position function and I've also graphed the velocity function for car B. And I can see visually that the velocity, if you can see this on your screen in green, is always above the t or the x-axis, and therefore the velocity is always positive. So what does that mean? Car B is also always traveling in the positive direction. Well, over the entire interval 0 to 8, but certainly over the interval 4 to 6. And so the distance that car B travels is just this difference. Well, there it is analytically. And I had to convert that into a number here to compare it with 80. And this turns out then that car A travels the greater distance. Here's a little bit of backup on my calculator screen. There's the analytical expression for the distance that car B travels. That's kind of cool. And here's the numerical approximation, 58.393. So once again, car A travels the greater distance. That's a cool problem. Very nice problem. All right, there's a part D. Are there any times in this interval 0 to 8 at which the two cars are traveling at exactly the same velocity? Well, what does that mean here? We have to equate v sub A with v sub B. Well, this would be pretty hard to do without technology. So here's how I did this. I know what the velocity of car A is. There it is. I have to equate that to the velocity for car B. So let's see. I did this in a couple of ways. I did this on the left-hand side using the calculator screen, and I used the command zeros. There's also a solve command, but I like the command zeros because you can put these values into a list and then you can refer to them. You can extract them from the list. So I got 3 values here, but we're going to exclude 0 because of what it says up here in the statement of the question. And just to sort of back this up, I have the velocity of car A And let's see, I graph the velocity of car B. I think this is B. I apologize right there. And I can see those 2 points of intersection. And what I did on the graph screen was I used the analyze graph routine, found those points of intersection, and let's see, do they agree? There's a t equal 2.591. There's a t equal 6.513. Indeed, they do. There are 2 times at which the velocity of these two cars is exactly the same. So I'll cross out the t equals 0, again, because that's not in the interval that was asked for, and we're looking good. Down at the bottom here, are there any times in that interval in which the two cars are traveling in opposite direction? Well, we've got this answer in a pretty straightforward way. We've already done quite a bit of analysis on these two velocities. We know that the velocity for both automobiles, for both cars, for both toy cars is positive. So they're both always traveling in the positive direction. So therefore, the two cars are always traveling in the same direction. There are no times at which they're traveling in opposite directions. How about that?
So
All right,
Steve,
Tom, go
Steve, here's
ahead.
a question for you on that one. So
Okay, shoot. Go
part
ahead.
E, and then I'll show folks how to do that graph on the 84. But
Okay.
so part E, they're both always going in the same direction. Was that a silly question, or was there anything about the graphs you have there where somebody might think, oh, there is some time where they're going in opposite directions?
Yeah, well, if you look at the graph, of course, there are some times when they switch. And so the velocity of one is beneath or less than the velocity of the other. So
Mhm.
one might think by looking at the graph that there are times when they are traveling in opposite directions. One might think that. Uh,
Yeah,
but that's not the case here. Yeah.
yeah.
So it's not
And,
really a silly question.
yeah, and in particular, I was looking at where the graphs of the velocities, one of them is there is an interval where one velocity is increasing and the other velocity is decreasing. And so that might be a tempting,
Oh,
oh,
yeah,
between 6 and 8, people might say, oh, they're heading in opposite directions there. But those are they're actually position, they're still moving forward. It's just one is
correct.
slowing down and one is
Yep.
speeding up. So,
Yep.
yeah. Okay, great.
Very good. Excellent. Okay. I will stop sharing, hand it over to you.
Okay.
There you are. Whoop, I'm sorry, Tom. Here we go. Let's try that again. There we go.
Okay. And right. So I'll try to share my 84 and hope it comes up okay.
Looks good.
Are you seeing that all right? Okay,
Yes,
great.
sir.
Just wanted to illustrate, Steve showed what that kind of reverse engineered piecewise linear looked like on the Inspire. It'll actually look very similar on a TI-84, but just what does one get at that? A lot of people have seen this before, but it's sometimes surprising to people that you can do these piecewise functions. So I'm in my y equals menu and just want to show folks how to get that. I'm going to go to the math menu and scroll down. And we go past derivative, integral, summation. When we get all the way down there to the bottom, we see piecewise. That's the thing we want. Enter that. And then it gives me a choice of number of pieces. Well, when I looked at this graph, it looks like there's 4 different linear pieces to it. So I'm going to increase that to 4. Press OK. And then it gives me this nice template where I can put both the formulas for each piece as well as the interval for which that formula will be good for. So in this particular case, I think for our first one, and we are doing, we're going to use X for time since we're in the Y equals menu. So that will be our time variable. So I'm going to put in a 5X. That's the formula for that first piece, and that's good for 0, and let's see, we want less than or equal to x less than 2. For that, I'm going to go to the test menu and scroll over to conditions, and you can see there's a nice shorthand that will fill in quite a bit of that for me. So I'm going to go down to number 6. And you can see, okay, 0 less than x, and x is less than, all I have to do now is put in the 2. And did I pick the right one? Maybe not. Let's see. I'm looking at it. Let me, I think I should have had a less than or equal to on that first part. So let me try that again. I'm going to go to test, conditions, and I think I wanted number 5 or number 7. Number 7.
Number 7. Yeah.
Okay. Third time was a charm. Here we go. Now we got an extra less than there. Let me get rid of that real quick. There we go. Finally, I've got it. Okay. And the next piece, let's see. I'll write it just a slightly different way. For each of these pieces, all I did was look at the graph that was given to me and get 2 points on that piece and figure out the line that goes through that. I came up with 15x minus 20 for this piece. That might be a slightly different form than what Steve came up with, but I think it's equivalent.
Mm-hmm.
And then we'll do from 2. And again, I'll hit that test menu, conditions. Let's hit number 7. And x will be less than, I think this is good up till 4.
Yep, correct.
And next piece here, this was the constant piece.
Yep.
So this was just 40. And that's going to be good from 6. Go to the test conditions, hit that number 7 again. 6 up to 8.
Yep.
See, you can really enter this fairly quickly. The time that
I think that was 4 to 6, Tom.
I think you are quite right, Steve. Let's see. I bet we can see I can edit it fairly easily. I'll just change the 6 to a 4. And thank you for catching that. And 6 there. Okay. And then finally, the last piece, I think I came up with 100 minus 10x, which probably looks quite a bit different than what Steve had, but I think it has to be equivalent. Okay. Yep. So we'll go to test, conditions. And this one, I actually want to go all the way to 8. And so this one I will use number 5 for. So 6 less than or equal to x and x less than or equal to 8.
Yep.
And let's get a graph of that. Oh, doesn't look too good because it's not a very good window. But if I think about the graph that was given, I can actually use it as a for a clue. I'm going to make my x-min -1 and x-max 9. That'll include that 0 to 8.
Gotcha.
Nicely with a little bit of buffer on the left and right hand side. And then let's make my x scale 1. And y-min, I think I'll go from -10 up to 50. That'll be plenty of space. I'll put a y scale of 10. And then let's try graphing again. Very nice. And the thing is, it is really easy. If you're someone like me, when you're figuring out those linear functions to make some kind of little arithmetic error be off, you're going to get a visual check. If you're matching a graph that's given to you, it's going to show you immediately what you need to fix. And so here we have a visual check, and we can trace on this just like any function graph. You can put in a particular value. I think there was a question, what was the velocity at x time 3? So right. I can type in 3 for x is our time variable. There it is, 25. I think that matches up right. Looks great. Okay. One other thing I was going to show is Steve had a a graph where he was looking at the velocity of both functions. We've got the velocity of car A here now. We can analytically go back to y equals and put in the velocity of car B. Now this one we need to calculate. I'm going to do it actually a couple of ways. Steve did it by hand. You know, he did the analytics and figured out, well, it was going to be 10 times x to the 2/3 power, I believe. Okay. Now I'm going to actually do it another way. We were given the position function. The velocity is the derivative of the position function. You know, I could have also done it by taking a derivative. So I'm going to go to the math menu, go down there to the number 8, do a derivative with respect to x. And here I'll put in the original position function, which was 6 times x, which is serving as our time variable, raised to the 5/3 power. And when you're graphing this, it's going to run through the x values from x min to x max. I'll just go ahead and put an x in here. Now, I haven't restricted the domain here. We're only interested in the interval from 0 to 8. We are going to get a little bit more graph than that because it'll graph for all the x values that I have. But the point I wanted to make here was, if you're doing a derivative symbolically, a way you can check it is plot it and also plot the numerical derivative. They should match up pretty well. So I'm expecting, if I've done the calculation right on y2, where I was doing that by hand, its graph should match up with y3. And that's just a general thing you can do for checking your symbolic derivatives that you're doing by hand. So let's go ahead and graph this and see if that actually works out. Now, that happened pretty fast. I hope you could see it. There was a red graph that came up, and then there was this black graph that came up. And the black graph is exactly on top of the red graph. So that tells me my symbolic, the fact that the numeric derivative that the calculator calculated and my symbolic derivative I calculated by hand matched up is a good check on my paper and pencil work. Can we actually find intersections on a piecewise graph in one of these? Well, let's just give it a shot and see. I'm going to go to calculate. And I'm going for an intersection. I think that was one of the later parts of the problem.
Yep.
First curve is the blue one. Okay. Second curve, it could either be the red or the black one. I'll go with the red one. And then a guess, well, let me go near where those two intersect. And there's that intersection point. Okay, so it came out really nice. And I could do a similar thing for that second intersection point. Okay. So I think that's it. I don't know if there's...
I have one more thing maybe we
Yeah.
could try, if you would. Would
Sure.
you go to the y equal menu just for a second?
Absolutely. Here we go.
Okay, let's turn off y2 and y3.
Sure. Here we go.
In y4, let's find the numerical derivative of y1.
Ah, okay.
So let's see if we can graph the acceleration function.
Okay, you have the piecewise one. Okay.
Yes, of the piecewise one.
All right. So let's go to math and
And then we've
derivative.
got another question in the chat, which I'll ask you about, okay?
Okay.
Which we can do.
This will be the derivative of y1. So I'm going to do alpha trace, that F4 up there. That's a shortcut to get in our list of y variables there. I'll
Yep.
get y1. So we're doing the derivative of y1.
Yep.
And people should keep in mind that the numerical derivative is really doing a difference quotient. And so it's, what would be really interesting is, what happens at those sharp corners in that
Absolutely.
graph. Okay, that's
Absolutely.
probably what you were anticipating. So let's take a look, see what it does.
Okay.
There's our original. I
How
think it
about
did a
that?
pretty nice job.
It did
Yeah,
a very good job, didn't it?
yeah, because the slope of each of these linear pieces is going to be constant.
Right?
And so we're getting a piecewise constant derivative. And where the original velocity was constant itself, that slope is zero. And so we're getting a stretch there that's zero. That all said, we might want to trace what actually happened at those sharp points.
Yeah.
Now,
Yeah.
so I'm going to go ahead and turn on the trace, and I'm going to up arrow to get onto uh, the looks like, I guess, magenta or pink curve. That's what it looks like to me. And look at that. It actually comes up. 4 was right in the center of the screen, and that's also where one of those sharp corners is at.
Yes.
And look at that. When you say right off the bat, that Y value there, that's supposed to be the slope of the blue curve at 4. And there's no way that can be right. There is
Right.
no, it's undefined there. And that's one of the things we have to be careful about. With a numerical derivative, you're not doing a true derivative. It's going to be a difference quotient. And so you'll get a value at these sharp corners uh, where we really know the derivative is not defined. Anywhere else, other than those sharp corners, we're getting a good slope value. So let me go ahead and trace over to x equals 6. Oh, my increment is not exact, so I'll just type in 6 for x. Oh, there
Oh,
we
that's
go.
interesting. Yeah.
We're actually getting a value there, but it's not correct. And
Mhm.
people may be wondering, well, why wasn't there a point plotted here? Well, that 6 value is actually falling in between, but I think it's because of the sudden jump in the values. Because I think under format, we've got detect asymptotes on, okay? And that detect asymptotes, it's for when that's on, if there's any sudden jump in the graph, it doesn't have to actually be an asymptote. Any sudden jump in the graph, it won't connect up. So it's trying to avoid connecting across discontinuities. And so we can see on our graph, even though we got a value when we traced over to say, I'll trace over to 2. That's another one of those bad spots, right? That's where
Yeah.
my
Yeah.
blue graph, it's a point of non-differentiability. If I go to the pink graph, I should not get a slope value if it was a true derivative. But let me put in 2 again. It's actually giving us an approximation which is clearly incorrect. Okay. All right. And that's where we have to use the tool up here, our heads, to realize that the numerical derivative is an approximation. It's going to be fantastic where the function is differentiable.
Yep.
But if you try to apply it on a point of non-differentiability, we shouldn't really expect it to give us back a reasonable result.
So, Tom, here's one more. We can actually do this in a couple of different ways, but let's do it in a cool way. Go to the Y equal menu once again, if you would. I'm going to set up the problem and then we'll answer it. If you would turn on curve or function Y2 and turn off Y4.
Okay. And now we'll have the 2 velocity functions.
Correct. That's what I'd like to do. I want to graph the 2 velocity functions. So let's see those. Beautiful. Okay, so now the question came in. Can you tell here, how do you determine, or can you tell which car traveled the farthest?
Ah, very nice.
Now, we don't have the position function for car A. We do have the position function for car B, but I think we could actually use this graph screen to answer that, couldn't we?
Well, let's see.
because the velocity, if we integrate the velocity, we know that's the distance traveled. The velocities are all positive. So can we integrate this piecewise defined function from 0 to 8 and then integrate the other one from 0 to 8?
Well, I sure think so.
All right.
I think the question, and we're at a time of the year in the course
Yes, where they might not know
where
how to
it's
do that.
interesting whether teachers have gotten to integration, definite integration yet on this. If they
Yes.
have, and in fact, part of this problem I think was intended to be a kind of nice precursor to that, and that's because you were asked, well, which car traveled the greatest distance between 4 and 6?
Yes.
And for car A, because the velocity was constant, we could do it just by, okay, well, it's constant 40 centimeters per second. We'll just multiply by 2 seconds.
Hmm.
Well, notice another, geometrically, that would be the area of the
Yep.
rectangle formed by the top of that graph lying over the interval from 4 to 6. So it's kind of a precursor to thinking about what definite integration does for us.
Yeah.
So yeah, let's see. I'm going to try the. Let's see. Let's see. We can probably calculate. Oh, we can calculate an integral right here.
Yeah.
So let me pull up number 7. The lower limit, let's do it from 0 to 8.
Okay.
This is for that piecewise linear. Shading it,
That's kind of cool.
and we should get a final result of, okay,
Exactly
200.
200. How about that?
Yeah, so that
Okay. So
means
that,
that car traveled 200 centimeters
okay.
during that time interval. Now we could do it again for, let's do a calculation of the integral. Well, let's see, I wanted to be on the red curve this time.
Yep.
We'll do the same interval, 0 and 8.
Ooh, how about that?
Ooh, looks
Pretty
like
cool.
car A just beat it. That's close. It was a close one. Okay. Very neat question.
It
But of
is a
course,
cool
this
one.
would not, this would make sense if you've gotten into integration in
Yep.
those applications. Yeah. So this is actually a problem that one could revisit, do
Yes.
it from the velocity and acceleration point of view, but then come back to it later when you're doing things like the distance covered by a car given its velocity and things like that. So
Now,
very nice.
we should mention that we had the position of this car B. We had that
Oh,
function
that's
given to
right.
you,
We could have just
right? So let's double check that. Can you do that on a calculator screen?
sure, yeah. Let's do the quit. And we had let's see, our function was 6 x to the 5/3, right?
I think so.
So that's the position function. So if we just took 6 times 8 to the 5/3
Right.
and then subtracted off 6
Well, it's zero,
and
right? It starts,
0. Right.
right?
Do here, I don't even have to put in the 5/3 there. Let's just
Right.
enter that. There's
Right
that
on the nose.
192.
How about that?
Matches up. So very
How
good.
about that?
Yeah.
Yeah, that's cool.
Yeah. And so these would all be, very good explorations or illustrations to do if we've got the integration going for us.
So this means that during the first 8 seconds, car A went farther,
Yes. Yeah.
correct? Yep.
Right. If we look back at those two graphs, um, let's see, I'm going to try to, if I go to y equals and then graph again. Okay. See if I wanted to erase those. I guess I could just do a wondering about a kind of
Clear.
way to clear those. Well, quick way, I think maybe window is I'll just make X-Men negative 1.1. How's that? Okay, and
Okay.
regraph. All right, we
Yeah.
get some new graphs there. There we go.
Okay.
The question is, so it looks like the red car, or car B, I should say. I called it the red car, but car B, it looks like it's going faster than car A between 0 and about 2.5, something like that.
Yeah, I think we found that point of
Yeah,
intersection,
so that's
didn't we?
when they
Yep.
were going exactly the same.
2.6. Yep.
So over this first interval from 0 to about time t equals 2.5, car B is ahead, but then car A is starting to catch up. So another interesting question we could ask would be, when did car A actually catch up?
Yeah.
And did it stay ahead the whole time then from there on out?
Oh, yeah. Yeah.
Because at the end, car A was slowing down, still going forward, but slowing down.
Yep.
RB was going quite a bit faster, but it never did quite catch up.
Yep.
Yeah.
Cool.
All neat stuff. All right.
Yep.
Was there anything else we should address from questions, or should I turn it back?
I don't think so, Tom. I think that's all I've got in the chat that Michelle has sent. That's all I
Okay.
see.
All right. I'm going to stop the share and turn it back over to you, Steve.
All right. Well, we don't have much time left, Tom, but I'm going to do part A, at least in number 2. Okay.
Sounds good. Yeah.
And we'll call it an evening.
Okay.
Let's see if I can do this. There we go. So this is a very interesting problem also. This involves a ball being thrown upward at time t equals 0 from an initial height. This is a variable of h sub 0, feet, measured in feet, and an initial velocity, another sort of variable here, v sub 0. And we're given that the height of this object, the height of the ball in feet, for t greater than or equal to 0 seconds, is given by this expression. And this problem, too, involves several different scenarios here in which we might have to find h0, we might be given h0 and v0, find velocity when it hits the ground, how high does the ball go, all sorts of very cool questions about this one. I will look at part A and we'll call it an evening. And we will post all of these, of course, with Curtis tomorrow. So the first part says, let's suppose that the initial height is 80 feet. Tom, help me here, but I think the usual way that the people explain this, we stand on a cliff and we're going to throw 80 feet high and we're going to throw this ball and we're straight up here.
That or we're reaching outside of a window of a tall building and
Have a tall building? Okay. Okay. And V0 is 40 feet per second. Find the maximum height of the ball. So there's one question here. And what's the velocity of the ball when it hits the ground? So that would be when h equals 0 feet. So, okay, it's kind of like I remember my calculus teacher sort of drawing this. So I'm 80 feet above here and I'm throwing the ball straight up here and it's coming down here. And I want to find the maximum height and I want to find what's the velocity when the ball hits the ground. Well, okay, first thing I'm going to do is to substitute in for v sub 0 and h sub 0. I know h sub 0 is 80. I know v sub 0 is 40. There's my expression for h of t. So how do I find its maximum height? Well, I have to find the derivative and I have to set that equal to 0. Now you're going to have to forgive me, give me a little literary license here. I've skipped a couple of steps, but I want to remind you of a few things here. If I'm going to be looking for places where there's a maximum value for this function h, I have to find places where the derivative is 0 and where the derivative does not exist. I have to find the critical points. There are no places, it sounds funny, but there are no places where the derivative does not exist. This is a polynomial and t is differentiable everywhere. Now we're only worried, really, remember, about t greater than or equal to 0. I take the derivative, I set it equal to 0, I've got a t equal to 5/4. Now, okay, practically, we understand this situation. We understand that there's a maximum here, not really a minimum. But to convince ourselves, to justify this, to explain our reasoning, I'm going to draw a sign chart. So the way that I've done this here is I've drawn the sign chart with values of t sort of at this level below the axis. It's kind of hard to see, but I have a solid square bracket in there, which means t could be equal to 0. I have one tick mark with a label where where h prime is 0, that occurs at 5/4. Now, I know we all have our own peculiar ways of figuring out the sign of h prime in that interval. I've always done this by arguing in general. And what I might even do is I might take this expression and I might even rewrite that to make it easier for me. For what I mean by that is I might take that 40 minus 32t and I might factor out, let's see, I think I might factor out an 8. And I might write that as 5 minus 4t, and I might even go farther and factor out a minus 8 and write that as 4t minus 5. And many of us find it easier to argue by looking at a linear expression in that form. Nevertheless, the sign of h prime is positive in this interval. The sign of h prime is negative in that interval. Now remember, sign charts are not acceptable justification on the AP exam. They're certainly okay to use. If you draw a sign chart, you must interpret that. So how do I interpret that? Well, let's see. The derivative of h is positive just to the left of 5/4. It's negative just to the right. The derivative changes from positive to negative at t equal 5/4. And therefore, there is a maximum, in fact, an absolute maximum at t equal to 5/4. What is that absolute maximum value? Well, I have to take that t equal 5/4, plug that back into my original expression. I think I did that. I got 105 feet, and bear with me here. I can do this a little bit with technology, and again, I use the TI-Nspire. Here's my function h of t. This expression is just solving the derivative equal to 0 for t. I got the t equal 5/4. And I evaluated h at 5/4. There's my 105. I feel pretty comfortable about this answer. Many of our students like to do this visually too, to back up or to justify, confirm our answer. Here's a graph of h of t, all right, h of x, letting x stand for t time. And I use the built-in routine to find a maximum of this function on an interval, let's say from 0 to 3. I can tell it's in that interval somewhere. There's the t equal 5/4, numerically 1.25, and there's the 105 feet. I feel really good about this one. I think we did this okay. So there was another part of this. What's the velocity of the ball when it hits the ground? Well, let's see. In order to do that, I have to find the time t at which it hits the ground. So that means I have to take this expression for h, set it equal to 0, and solve. Oh, holy Toledo. I don't think I could factor that easily. So I had to go to the quadratic formula. I got two possibilities, but I think with the minus the square root of 105, we get a negative value for t, so we can throw that out. So the time at which the ball hits the ground is this, 145 plus the square root of 105. What's the velocity when it hits the ground? That's the derivative of h at that value, which I called a. There's the analytical expression. There's the numerical expression. And son of a gun, this is really cool that you can do this with the Nspire. Here are the zeros of h of t. Look at that. There are my two analytical expressions given to me by the TI-Nspire. And Tom always reminds me to remind everyone that this is the CAS version. And look what I've done here. I took the second value in this list. That's the positive value of t. I evaluated the derivative at that value, a. There's the analytical expression that I got. There it is, right there. There's the numerical expression. That's pretty cool. So there are a variety of questions that involve this situation with this expression h of t. I hope that you'll try to solve those without looking at the answers first, and we'll post all the solutions, or Curtis will post those solutions sometime tomorrow.
So,
So thanks. Go ahead, Tom. I'm sorry.
well, Steve, it looks like if you can stand it, since we got a late start, we could stay just a little bit longer, if that's okay with you.
Okay. Sure. You want to take a look at part B?
Well, actually, what I would was hoping to do is maybe show just a little bit more technology on this one.
Okay. Go ahead.
Okay.
Excellent. Go
All
ahead.
right. So I'm going to go back and share my 84 again. See if that comes up okay. Great. Okay. And
Looks
just,
good, Tom.
with these particle motion problems or rectilinear motion, we got something moving in a straight line. It's a great place to make use of the parametric feature.
Yes, sir.
Your calculator. And so to get into that, we go to our mode. And normally, I'd say about 90% of the time or more, you're in function mode. That's gives you your y equals a function of x menu. You change that over to parametric. And then if you go to the y equals menu, you're going to see something that looks a little bit different. Okay, you're going to have pairs of functions of t. So it'll be like an x1 of t, y1 of t, an x2 of t, y2 of t. In this case, we really have motion in just one direction. So what I've done here is I've made x1t just equal to 1. And so the x coordinate will always be at the same x coordinate. And then since we're throwing the ball up and down, I made y1 of t that function of t that we were looking at in that part A. So there's that 80 plus 40t minus 16t squared. Now in my window, you'll see that I've got settings for starting t value, t min is 0. I'll make the t max, let's just go say to 5 seconds, okay? And I've set the t step to 0.1. So we're going to see the position of the ball every 10th of a second between 0 and 5. And then notice I put the x min 0, x max 2, that puts 1 right in the middle. So the center of the screen is where we'll see things going up, down. And I set y min to minus 10 and y max to 110. I think that was a good range for seeing what was going on here. Okay. And now if I go y equals what you would normally have for a graph line would just be a solid line, okay? And so if we graph this, we don't really see much other than that's basically the entire path of the ball traced out. And since it was going up and down, we just see a kind of a vertical line segment here. What really gets nice is if we go back to y equals, and I'm going to change the graphing format here from a solid line, to a ball. It's actually going to look like a ball that's moving up and down. Okay, so let's see what this looks like when we graph. It happened very quickly. But you saw the ball go up a bit and then come back down. If we actually trace, get this little crosshairs, we're actually seeing every 10th of a second, we're seeing the ball go up. And it kind of hits, let's see, I forget, where was that maximum value?
The max was, I think, 105 feet, Tom.
Yeah, at what time was it at?
It was at time 1.25.
Okay, interesting. So I'm at time 0.8. Okay. It went up a little bit more. Oh, I'm at 104, 1.1, 1.2. I'm at 104.96, 1.3. Oh, but we skipped over the 1.25. I could actually type in 1.25 and see, well, where was it exactly at that time? Ah, there's your maximum now. And then if I keep tracing, now it's starting to fall. And I'm going to watch as it gets close to the ground. I was taking a mental note, I think, of that value you got. It was something like square root of 105 plus 5 all over 4.
Yes, sir. That's
And
correct.
so I just did a little bit of mental arithmetic. Square root of 105 is about 10, a little bit more than 10. So 10 plus 5 over 4, it should be hitting the ground just a little bit before time t equal 4.
Okay.
Oh, look at that. I'm at
How about that?
3.8. Yeah, okay, now it's going underground. Okay, so that's a nice reality check there.
Yes, it is.
Okay. The other thing I wanted to check is right before it hits the ground, let's see, at time 3.7, the Y value is 8.96. And then I'll just go 1/10 of a second more, and I'm almost on the ground.
Yep.
So it dropped about 8 feet in that last 10th of a second. So that means it's going down about 80 feet per second.
Which is exactly what we found,
Yes,
wasn't it? That's
exactly.
really
Oh,
cool.
right. Yeah.
Yeah.
So one other feature I would show here is this ball feature is kind of nice. There's another version of it. So I'm going over there to the format of how to plot. And that is a ball with a line. It'll leave a trail behind. So that's where you see that little thing to the left of the circle. That just means it's going to leave a trail. Okay, so let's see what this one looks like. So I'm going to graph again. And you see it's left a trail. So you saw both the ball and the trail. And now if we trace, we can actually see it going up and down that line.
Hey guys, we've got a
Yeah.
question in the chat.
Oh, yeah.
Yeah, Gerald wasn't feeling like his answer got answered specifically about which car went further during the first 8 seconds. Do you guys think you can circle back there?
Sure. Yeah, I think so. Let's see. Steve,
Before we do that one, Tom,
Yeah.
can we try one more thing here and then we'll go back to that?
Okay,
Could you go to the Y equal menu?
sure.
So we recognize that this ball, this object is traveling in a straight line.
Mhm.
But sometimes we can get a little bit better visualization, I think. If we change that X1 and T, can we write that as something like T divided by 5?
Let's see. Yeah, we could. Is there a reason you wouldn't want to just use regular T? Or
Well, that will make it quite wide. I was thinking of if T goes between 0 and 1, then you'll kind of see the arc of the ball in some sense. I was thinking.
okay.
I don't know. Let's see what happens with that.
Sure. Okay. T divided by 5.
Because I think you had T going from 0 to 5. So this will go from 0 to 1. So let's see what happens with this.
Okay.
Yeah, there you go.
Yeah. Yeah. And the reason I was asking about just using regular T is it would actually then show you it basically matches up with the graph that you were showing.
Yeah.
Because you were plotting the height of the ball as a function of T.
Yep.
And of course, I would want to change my T value. So let me just do that really quickly. I'll just put in a T there.
Okay.
And let's see, for window, probably need to go from X-min 0 to maybe 5 or something like that will be enough. And that's actually, it's matching up with a function graph. So we
Correct.
just X is T and then Y. So another nice one. Okay.
Okay, so I'm not
Back-
sure, I'm not sure exactly what the question is, but is it possible for you to go back to function mode and show those two velocity graphs?
Yeah, let's try that. So I'll go back to
Okay.
function. And
So I think there was a correction of what Gerald was wanting some better explanation on was his first question, which is there a time at which the cars are at the same location? And another,
that they're at the same location.
yes. And Gerald
Oh,
did also request that maybe we could include these notes within your documents after live stream.
okay. Those
So,
notes being from the questions from the chat, or
Yes, from the questions from the chat.
okay.
so if you just graph those two, I think, Tom, that would be sufficient.
Oh, I need to get my
Change the
window
window.
better. Yeah.
Yeah, okay, sorry about that.
Oh, no problem. I'll make
So,
the X's go from 0 to 8.
Yep,
And then let's see, Y min, Y max. I think 50 probably works.
50 was good. Yeah, I think so, Tom.
There we go. Yeah, that looks pretty
Okay,
good.
so if the question is, are there any times with the exact same position? That's a tougher problem.
It is. It is. It's
And
we have the language of integrals, we'd be asking at what time would the definite interval from 0 to that time give you exactly the same areas under those two curves, right?
right,
Yeah.
right. So that sounds like a typical AP question, like set up but do not evaluate.
Yeah.
Right, right. So are there any times it's quite possible? And we think there is at least one time because Tom made an argument that car B starts out faster than car A, but we know that car A ends up farther after 8 seconds. So there must be a time at which they are at the same position.
Now,
At
we
least
could
one
see
time.
it. We could see it graphically if we graph the definite integral function
Oh, that would be cool.
for the piecewise against, because we have the other position.
We have that. That's right. Yeah, we could do
And
that.
then so we could see kind of where those two graphs intersect. That would be
Yep.
cool. Yeah.
That'd be
I think time probably doesn't permit for us to do that, but if that makes sense,
Yep.
we would be doing like a definite integral from 0 to X of Y1.
Yep.
That would show us the position function for car A, and then we could compare that to car B. Yeah. And we'd want to set up a different graph, I think, because the X min X max will be the same, but the Y min and Y max is probably different values would be
Yeah,
appropriate.
at least up to 200.
But
Yeah.
that'd be nice. Yeah, that would be kind of cool. Yeah.
Yeah.
All right.
Okay.
I'll stop share, turn that back over, and I think
Okay.
that probably wraps it up for us
Yeah.
tonight.
Thank you very much, Michelle.
Thank you both. I appreciate y'all. Have a great night, everyone.
All right. We'll see you in January.
Okay.
Very good. Thanks, Tom.
All right. Bye-bye.